Today, Georges Meynet. It's really a pleasure to welcome Georges as our speaker for the third Quid Ultra Colloquium in 2022. Georges is one of the leading scientists of the Stellar Evolution Group of the University of Geneva, who has been really a reference point in the field since many, many years. And after a diploma in physics at the École Polytechnique Fédérale de Lausanne and a PhD at Geneva University, Georges did a postdoc in Brussels at the Université Libre de Bruxelles. And since 2006, he became professor at the Department of Astronomy of the University of Geneva. And Georges is an internationally recognized expert in stellar physics, stellar evolution, stellar populations in galaxies, nucleosynthesis, the nature of progenitors of different types of core collapse supernovae. And is also very active in promoting astronomy towards the general public. He has contributed to the building of a public observatory and a planetary walk in Saint-Luc-Val-d'Annivière. And he's now promoting a project on a supernova fountain. And this appears to be a very original and interesting idea. And we all wish to become a reality soon and to visit this. And the research activity of Georges and his group in Geneva is presently focused on the physics of the first stellar generations in the universe, and in particular in connection with the understanding of the origin of carbon-enhanced metal-poor stars. And he's leading an advanced ERC project called StarX, Stars at the Extreme, aimed at producing new models of the first generation of stars and investigating their properties and potential observational signatures. So we all look forward to hearing his views on this in his talk. So Georges, I leave the floor to you. Thank you.
Thank you very much, Rafaela, and thank you to the organizing committee for giving me this opportunity to present some recent results about stars at the extremes, which are either stars formed at the very beginning of the universe history, stars rotating very fast, like spinstars, or having extremely large mass. So I would like to tackle different topics. Actually, I will, if I have time, address 7 different topics before to leave the word to Leonardo da Vinci at the very end. And of course, I will be very brief on each of these topics, but trying to give you some points, some ideas, and some recent results that we obtained with the StarX team in Geneva. And you can see the people belonging to the StarX team with some extension in other parts of Geneva, like with Arthur, José, Eoin. And also now we are collaborating since a few years with Boyuan Liu and Volker Brom in Texas. So let us begin by saying a few words about what are the challenges for stellar evolution nowadays. First of all, we can say that stellar physics lives in a kind of golden era, in my view. The reason is that we need to know very well stars in order to progress in very topical question in astrophysics. If we want to know what are the characteristics, the properties of a planet, of an exoplanet, you need to very well know the stars. If you want to know what are the progenitors of the binary black hole that can merge and produce gravitational wave, you need to know, of course, stellar evolution. And if you want also to link a given luminous transient event like a superluminous supernova to a star, you need to understand what was the history of this star. So we are living really in a beautiful time for stellar physics. But do we have the needed model that are requested to progress in these different fields nowadays? We can say that stellar physics is a major field in astrophysics. It has a long history, but nevertheless, it is still a very complex field. And we can say that nowadays, our stellar models are not sufficiently accurate, reliable, in order to be really, I would say, useful in a very quantitative way for all the questions I was mentioning before. And why it is like this? Because if most of the time a star is at mechanical equilibrium, which of course can allow to make very simple model of stars, even in these stages of hydrostatic equilibrium, there are many hydrodynamical or magneto-hydrodynamical processes which are difficult to model. I cite here convection, of course, but also the way the stars are losing mass by different processes, from line-driven winds to reaching very high surface velocity, how rotation drives turbulence inside stars and drive transport of angular momentum of chemical species, the impact of a magnetic fields, which can be very important both in the interior of a star, but also at the surface. And of course, a whole question of multiplicity that add new processes like mass transfer, tides, common envelope, merging processes. So all these makes the stars complex to model. It is even more severe by the fact that all these processes interact between them. We cannot isolate one of them. And just to give you an example, typically if we want to compute the evolution of a closed binaries, it's obvious that in that case, because of the tides, the two stars will be synchronized, and the short orbital period will also impose a short rotation period. So the star will rotating fast. This will drive chemical mixing that can make the star to have an evolution very radically different from the classical one. But for this to be studied, we need to understand the physics of rotation and also both the physics of the binary evolution. All these processes will produce a huge variety of stellar models. And of course, even with 1D stellar evolution code, it will not be possible to explore all the, I would say, the different initial conditions and even the different physical inputs. So here we had with José Gros and Erwin Farrell the idea, which is not a new idea actually. It has been used by Cox et Salpeter a long time ago, by Giannone in a very famous paper where he was looking how a star evolved from the red to the blue by changing the mass of the core. We had the idea of computing what we call snapshot models. What is this? Actually, it's like to start from a stars in a kit. In the kit, you have three big elements. You have to choose at which stage you want to make this study, because it's not an evolving model here, it's more a structure model at a given time of its evolution. So you choose which stage you want to study. Then you choose the mass of the core and you choose the mass of the envelope. So you have three choices here. And one example of these snapshot studies is given by the plot here on your right. Actually, you can compute the effective temperature and the luminosity for stars having a given helium core mass. Typically, if we take the six solar mass, so I think it's one of these lines here, and you can look at how the effective temperature of such a star will change when you add a more and more massive hydrogen-rich envelope. So of course, when you go toward the right on the horizontal axis, you have that the mass fraction of the core with respect to the total mass is decreasing because you add more and more mass in the envelope. So at the beginning, when you have a naked core, you have a very hot star. Typically, if you have a star with a 6 solar mass helium core, it will have an effective temperature of 5. If you add a small hydrogen envelope, even only half a solar mass, it will make the star to become a red supergiant. And for a long, I would say, a very different type of envelope mass, you will still remain a red supergiant. You can add even an envelope of 40 solar mass. It will still have an effective temperature of 3.6. So here, there is a lot of degeneracy, I would say. You can have many different star structure with the same helium core, but with very different envelope, which produce the same effective temperature at the end. And here we have a kind of B-stability where when you add a little bit more mass, you will go back to the blue. Actually, you have a kind of pseudo main sequence stars, which will be, I would say, triggered by a very strong hydrogen shell burning. An interesting application, which is not so new, but which is particularly interesting because we can do it in a very quantitative way. And this is a little bit outside the topic here of the first stars, but I wanted just to discuss this, is the fact that it's very difficult from the luminosity and the effective temperature of a progenitor of a type 2p supernovae to guess what is its final mass, what is its actual mass. Let us take, for instance, the supernova 2012AW from the series, from the list which has been gathered by Davis and Bizot in 2018. So we know the effective temperature and the luminosity of the progenitors. From the luminosity, it's possible to infer the mass of the helium core because there is a tight relation between the luminosity and the mass of the helium core, and the mass should be around 4.2 solar masses. But now, because of this degeneracy and because we have here a red supergiant, actually we have a red supergiant and we can add very different type of mass of the envelope without changing neither the luminosity, neither the effective temperature. So that at the end, the final mass can be everywhere between, let us say, 5 and 35 solar mass. Of course, if we have spectroscopy, we can have access to the surface gravity, and in that case, narrow a lot the domain. Another interesting, I would say, application of this snapshot is that in addition to the stage, the mass of the core, the mass of the envelope, we can also make some experiment by changing a little bit the profile of some abundances inside the star. And actually, if we look at here, we have the profile of helium on the upper left diagram as a function of the mass in the 15 solar mass stars. And we are in the middle of the core helium burning phase. And at the beginning, the star is a blue supergiant, so luminosity around 4.9, and it will be a hot star. Now, by hand, we can add a little bit of helium, changing a little bit the profile of helium. And actually, what will happen? The star will no longer be a blue supergiant, but will evolve in a red supergiant stage. It will become, it will pass from 45 solar radii to a star with more than nearly 562 solar radii. It's because, you know, when you add a little bit of helium here, actually you will have to decrease, of course, the quantity of hydrogen. And the hydrogen shell will have a hard time to compensate for the luminosity loss at the surface. And the star will react by contracting the core. But if you contract the core, you will expand the envelope and you will get a structure which is much more expanded due to the virial theorem. So you can see here an example where a tiny change has a tremendous importance on the position of the star in the Hess-Pungosser diagram. And we have to keep in mind when we speak about stellar evolution. Now let us come to the case of the first stars. So the first stars are stars that we cannot observe, I would say directly at least. We can only have some indirect, I would say, flavor of them or hints of them. We know that they must have existed, of course, because we should begin by the first stars. But of course, the model that we do cannot be compared with individual propulsion-free stars that we could observe, at least at the moment. So, but we can still, but these stars are still very important because they are important in order to know, for instance, what is the contribution of this first stellar population for the reionization. How they will impact the early phases of the chemical evolution of the galaxies, and some of them can indeed be important for producing the carbon-enhanced metal poor stars. It's important to model them to be able to recognize maybe some in the integrated spectra of starbursts, which are mainly containing propulsion-free stars, to recognize such propulsion-free starbursts, and also to be able to recognize some signature coming from propulsion-free luminous transient event or event from merging with black holes coming from propulsion-free population. Of course, in order to model these stars, an idea will be to follow the following line of reasoning. Actually, since we cannot observe these stars, the best way is to try to use the physics, then when applied to the modeling of stars in the solar neighborhood, give, I would say, a good fit to as many observational constraints as possible. And actually, we have in the last years, last decade, I would say, compute complete grid of stellar models for nearly the whole mass range, from the low to the high mass range, for metallicity from population free to over solar metallicity, with a physics which is the same, except of course that the processes, when they depend on the metallicity, are adapted to each metallicity. Typically, the mass loss rates will be decreased when we go toward lower metallicity, but typically, otherwise, the physics is homogeneous to some extent. And here I present a recent grid for population-free stars that contain the physics for non-rotating and rotating stars that we have used in the grids by Sylvia Ekström for the solar metallicity. This grid at solar metallicity can reproduce some well enough some observed features of massive stars in the solar neighborhood. Of course, it's not perfect. There are some, I would say, lights and shadows, but nevertheless, we know which are the consequences of this physics at solar metallicity. And now we look, what are the consequences for population-free stars? So you have here the grids, and I would maybe make a remark in the models with rotation. When we speak about rotating models, it's very important to specify what rotation means, because rotating models can mean a very large diversity of outputs, depending what is behind this term of rotation. So I will just tell you that in the rotating models here, we account for hydrodynamical instabilities driven by rotation. Hydrodynamical instabilities, which are the main ones, are meridional currents and the turbulence due to the gradient of omega, shear turbulence induced by rotation. And this is what we have included here. In this model, for instance, we have not included magnetorotational instabilities or magneto-hydrodynamical instabilities, like, for instance, the telescopic dynamo. But we have this hydrodynamical instability, which are accounted for. So this is the first point. The second point, we can see that whatever we have rotation or not, the tracks remain in the blue. And this has a very, I would say, easy and very well-known explanation. As you know, if we take typically the 20 solar mass stars at population free, at the beginning, there is no cyano element. So the star will burn hydrogen with a PP chain, but the PP chain is not efficient enough to prevent the star to continue to collapse, not to collapse, to contract. And this contraction will continue until the point where the temperature becomes high enough for activating triple alpha reactions, and thus to produce a little bit of carbon that will then allow the star to continue its burning of hydrogen through the cyano cycle. But this has a tremendous consequence. It means that the hydrogen burning in population-free stars occurs at much higher temperature than in more metal-rich stars, because the star had to contract. So the temperature is high, and is high enough to be nearly the one of the helium burning. So it means that at the end of the hydrogen burning phase, the core has to contract to reach the temperature of helium burning. It has not to contract a lot, because we are nearly already at such a high temperature for helium burning. So this relatively weak contraction releases less gravitational energy, and moreover, the envelope is more compact. All the star is more compact in population-free stars by a factor of 3 to 4, depending on which mass we are considering. So it's a big factor, for factor 3 or 4. So the gravitational energy, the bonding energy of the envelope is greater, I would say. So it's more difficult to expand. So you can see that typically I have just shaded here in cyan the part covered by the core helium burning phase. It remains quite in the red, in the blue. For the rotation, you change a little bit the gradient, as I showed with the snapshot model a few minutes ago, and it extends a little bit toward the red, but it does not change dramatically. It has a consequence, of course, for the binary evolution of these stars. You need to be much closer in order to have a mass transfer, for instance, because the radius keep much more modest than at high metallicity. We look at the impact of these models on reionization, and you have this plot here on the right, which shows the number of ionizing photons per solar mass locked into stars. And the ionizing power has 3 colors, because we are considering photon for ionizing hydrogen, for ionizing helium, and for ionizing helium 1 time ionized. And the different symbols correspond to different models computed with and without rotation, with different size of the convective core. And of course, you have here dependencies with the IMF. On the whole, we obtain that accounting for rotation increase a little bit the ionizing power by 25%. If you increase a little bit the core, but in a moderate way, you can increase it by 20%, making flatter the IMF in this range here, can increase the ionizing power by 20–30%. Of course, here we are considering moderate rotation, 0.4 the critical velocity on the SAMs. If you are considering faster rotating stars, it can change a lot because you can have homogeneous evolution. And in that case, the star will remain in the blue and will be nearly a vertical line at a nearly constant effective temperature. And in that case, you can increase a lot the ionizing power by, in some mass range, by at least 1 dex. Let us say now a few words about the Spinstars. Spinstars is a name, is a kind of shortcut for 3, I would say, properties. It should be a massive, metal poor, and fast rotating stars. And each of these properties has an importance. Why rotation is important? Rotation is important because it drives turbulence that transport chemical species, transport angular momentum. Why at low metallicity? Because at low metallicity, everything being the same, rotation has more impact in the mixing. It will be too long to explain exactly in all detail why, but there is at least one reason that is easy to explain. The stars are more compact. And so, in particular, the radiative envelope, where the mixing is important, of course, by rotation, because anyway, in the convection, it's anyway there, but it's what will change most the evolution is the mixing in the radiative zone. And in this radiative zone, it will be, this radiative zone will be more compact, so less extended. And as you know, the time scale for a mixing process by a diffusion, it's the length scale over which this mixing operates to the square, divided by the diffusion mechanism, by the diffusion coefficient. If this coefficient is the same for 2 stars with the same mass, with the same rotation, then, of course, the one which is more compact, which will be much more rapidly, I would say, mixed. And since metal poor stars are very compact, they are more mixed. Also, massive stars are important because the diffusion mechanism for rotation scale with the thermal diffusivity. And if you use homology relation, you can see that the diffusion time scale, which is proportional to the thermal diffusivity, will scale as the inverse of the mass at the power about 1.8. So you increase the mass, you decrease the mixing time scale. Of course, if you increase the mass, you decrease the main sequence time scale. But the main sequence time scale is inversely proportional to the mass at the power 0.8 for the very massive stars, or for the massive stars. So the decrease of the main sequence time scale is slower, shallower than the decrease of the diffusion time scale, mixing time scale. So we expect that more massive is a star, more mixed it will be, everything else being the same. And this has tremendous impact for nucleosynthesis. It can be also invoked for explaining the CMP no star, at least the one which are enriched in nitrogen. It has an impact, as we have just mentioned, on the radiative feedback about the ionizing power of these population-free stars, and probably it has an impact on the mass loss when the star reaches a critical velocity at which is the velocity at which, of course, the centrifugal force balances the gravity, and where some disk, I would say expanding disks can be produced at the equator that can be lost by the star, by the way, so it can be a mechanical mass loss process. And you have the type of supernovae, which can be depending on the rotation. So I will just maybe here discuss one interesting consequences, new consequences, I would say, of this spin star. This is an old graphic showing how rotation impacts the chemical structure at the end of the helium burning phase. We have the rotating models on your left and the non-rotating one on your right. It's a 40 solar mass star, or 60 solar mass stars at very low metallicity. It's not a proportion free here, it's very low metallicity. The point which is interesting is to see the profile of nitrogen, which is, of course, boosted in the rotating models. The reason for that is that in the rotating models, we have some carbon and oxygen produced in the helium core that can diffuse in the hydrogen bonding shell and can boost a lot the production of nitrogen. And this nitrogen can diffuse into the helium core and produce a bump of neon-22. And as you know, at the end of the core ion bonding phase, neon-22 capture alpha, which produce neon-22 alpha N reaction. There can be also alpha gamma, but we are interested in alpha N reaction. And the neutrons, which are released by this reaction, can be used to produce, can be captured by iron seeds and produce S process element. It's probably not the case at this low metallicity here, but for higher metallicity, this primary nitrogen production can be accompanied by a primary neon-22 production and by an important boost of S process elements. And this has been studied by many different authors. But there is an interesting new consequence. It's about the P process. So P element are in contrast to S and R process element, which are neutron-rich isotope. The P process are proton-rich isotope. So in the chart of nuclide, where the isotopes are ordered as a function of the neutron or of the number of proton on the vertical axis and the number of neutron on the horizontal axis, as here, then we have that the P process isotope will be on the other side of the valley of stability here of the isotopes. So they are proton-rich. And typically, in the following, I shall consider strontium-88 as a kind of a representative element of the S process, and selenium-74 as a representative element for the P process. Just a point, the P process have low abundances in the solar system, typically. They are much lower by about 1 order of magnitude with respect to the S and R process elements. The typical, I would say, sources for these processes has been suggested by Marcel Arnoux a long time ago as the hydrostatic oxygen neon burning shell in massive stars. And also their production by type 1a supernovae has been studied at least by Claudia Travaglio. But here we have looked with Arthur Chopin to another possibility, invoking spinstars. You have here actually the profile inside 225 solar mass stars at a metallicity which is not so low as before, 0.001. And this is really, it's a more advanced stage. You have actually nickel at the center here. The shaded area correspond to the part of the star that will remain locked into the neutron star, probably here. And what I want to mention is the fact that this line, this light green line, represent the variation inside that model of the S process element which is strontium-88. This is the non-rotating case, and in the rotating case, for the reason I have just explained a few minutes ago, you have a boost, by nearly 2 orders of magnitude in this model here. Why I show you this S process element, I want to speak about P process, because the S process elements are in general the seed for producing P process. Actually, what will happen is that some photodisintegration will take off some neutrons from these very rich neutron rich elements and actually will produce by some recombination some P process. This is shown in the next diagram here. In this plot, we have just a little part of these 25 solar mass models. It's the region between, let us say, 1.5 and 6 solar mass or 5 point something solar masses. And this is mass fraction. The dotted line represents the initial abundances on the 0 age main sequence of these metal poor 25 solar mass stars. The black is for the strontium and the red is for selenium-24. Now, if we let the star to evolve, at the beginning of oxygen burning, we have this enhancement of strontium-88, which is nearly flat in the zone of the star. And for the selenium-24, at the moment, just at the beginning of oxygen burning, nothing has appeared. So selenium is nearly 0. At the end of the evolution, when we are at the supernova, the pre-supernova stage, we have the dotted line. So you can see that part of the strontium has decreased and selenium has increased, exactly in the line of what has been proposed by Marcel Arnoux, namely a production in the oxygen neon shell in massive stars. But actually what we obtain here is that what remains the most important phase during which this P process could be produced is the explosive nucleosynthesis. And the explosive nucleosynthesis is shown here by the continuous line. And you can see that a lot of strontium will be destroyed, and some of them will produce this bump of selenium-24. Of course, it's not only strontium, but it's just an example here. Actually, here you have on the right the production factor of P process elements for all the P process. The black line corresponds to the non-rotating models, the blue to an average rotation, and the red to a fast rotation, and the green to a kind of a mean value obtained by assuming some velocity distribution of these stars. There is 3 plots because we tested with different value for the rate of oxygen 17 alpha gamma, which has an importance for the S process elements. I will not go into these details. If somebody has a question, I will answer at the end of the talk. But nevertheless, if we take, for instance, this plot, you can see that the P process can be boosted by 4 orders of magnitude with respect to the non-rotating case. So it may be that in addition to the sources that I mentioned at the beginning, Spinstars could be interesting sources of P process element. I go now to the thema or the topic of the very massive stars. By very massive stars, I mean stars which have initial masses above, let us say, 150 solar masses, and which can go up to 200 or maybe more, 500 solar masses. Actually, if we look at the Hesperus diagram of the Tarantula Nebula in the LMC, we can see that there are a few points which are above the 200 solar mass track. Of course, we are not sure that these stars are single object, but if they are single, it would correspond probably to 300 solar mass stars. So there is some interest to look at these stars. I would like to discuss 2 points about these stars. The first point is that the evolution of these stars at solar metallicity, or even at the metallicity of the LMC, is governed by the mass loss. It's the mass loss which is the main dominating effect. But at low metallicity, rotation can be a very important effect. And I would like to illustrate this by showing this example of computation of a 250 solar mass stars at very low metallicity. It's not population-free, but it's 10⁻⁵ in mass fraction. And you can see how the rotating model behave in the Hesperus diagram and how the non-rotating models behave. It's very different. Actually, the rotating models, whose Kippenheim diagram is shown here, has a very huge convective core, also a very huge convective core during the helium burning. It has an evolution which is similar a little bit to homogeneous evolution. And because it remains very long in the blue, it loses relatively little amount of mass because in that region, there is a metallicity dependence which prevents the star to lose a lot of mass. Even if it enters into the W, it becomes a Wolf-Rayet stars. So it loses these rotating stars little mass, a few, maybe 10 solar masses, something like this, maybe 20. While the non-rotating stars spend much more time during the red, or let us see in the redder part of the Hesperus diagram, and here it loses 100 solar masses. What is interesting is that these stars here probably, both stars encounter the pair instability, which is due to the fact that, of course, when you reach typically oxygen burning, the photon have enough energy to create pairs of electron and positron, and this has to, and this tend to destabilize at least the region where this occurs at a sufficiently high rate, because you remove photons which are so important for those stars to balance the gravity, and the adding of the electron pair does not compensate for this. So it destabilizes the star and it can trigger the collapse. But in that case, in the non-rotating case, the collapse can trigger nuclear reactions which can make the star to explode completely, which will destroy completely the star in a pair instability supernovae. There will be no remnant. While in that case, the core is too massive to be blown up, at least from computation that has been made by others than in this work here. And we expect that in that case, a black hole, a massive black hole will be formed. Another aspect that I would like to tackle is this question of the mass gap of black hole. As you know, these very massive stars, some of them, and I just mentioned that a few minutes ago, some of them will leave no remnant at all. It means that there will be an interval where there is no remnant, so no black hole mass to some extent. And this mass gap of black hole has been determined by, of course, by theory, to be between 55 and 130 solar masses. You know, it's much smaller mass than the 150 and 250 or 500 that we are speaking before, even if a 150 solar mass probably will become a per-instability supernovae. But it accounts for the fact that before to explode, the star will go through a phase of pulsational per-instability that is expected to remove a lot of mass. So it means that you can start from a 150 solar mass and at the end with a relatively little amount of mass because of this loss by pulsational mass loss rate. So the mass gap here in terms of black hole mass is of course much smaller than in terms of initial mass, let us say. What is interesting is one event, the gravitational wave event 19521, which is here. If we look at the mass of the individual black hole, at least one is completely inside the gap. The green point corresponds to the black hole after the merging. But here, the two black holes are here. Even the second one is in mass gap, but of course, but here the error bar can take it out. So at least for this case, we need to explain it. It does not, I would say, confirm the prediction here. But of course, some of this prediction has been made based on pure helium stars. And actually, there is a little bit of a difficulty when you start from pure helium stars and you look at the further, I would say, evolution, because you miss the possible interaction between the helium core and the envelope or the hydrogen shell. And typically, these interactions can be important in, I would say, governing especially the advanced stages of the evolution. Here you have a Kippenhahn diagram of 85 solar mass stars for a population-free star. It's non-rotating, but nevertheless, you have at a given point, which is indicated by the red arrow here, some kind of interactions between the convective helium-burning core and the hydrogen shell. Typically, due to some overlap at some points of the region which are mixed in the convective core and the hydrogen shell, you have some carbon which is injected into the hydrogen shell, even without rotation here. And this boosts the hydrogen shell and produce a decrease of the size of the convective core because of the restructuration of the star due to this new way of producing energy. And it happened that the carbon oxygen core at the end here will be around 30, 35 solar masses. And below, let us say 40 solar masses, according to model by Farmer, it seems that this star will avoid to lose mass by pulsation per instability. So now, if we plot typically these stars, these 85 solar mass stars, without rotation and for population free, it has a core which is below this limit where the pulsational mass loss is triggered. So it is probable that this star will keep its 85 until the end of the evolution. And maybe if all this mass will be swallowed by the black hole, it will produce a black hole in the mass gap. So it's a way, it illustrates first two things, that maybe this black hole could come from very metal poor massive stars. And this has also been, I would say, invoked by Liu and Brom in this 2020 paper. Of course, we can say that here maybe the situation is different for this black hole because it is in binary system and maybe it comes from binary evolution with mass transfer and so on. But it can be also that this binary black hole is come from dynamics. And actually in work with Boyon Liu and Volker, we derive the statistic of binary coming from the first stellar clusters produced in mini halo. And it may be that the number of isolated binary that are that will evolve as a closed binary from the beginning is very low. And in order to have a merging event, you need to have dynamical evolution. So you can imagine that the two black holes are much more, I would say, separate, and it's an interaction with a third body that can make tighter the binary black hole. So it means that maybe the single star in that case could not be completely irrelevant too. So I will say a few words about the supermassive stars now. This is another story. It's in order to understand the progenitors of very massive black hole observed at very high redshift. And this is the main, I would say, triggered for the question of these supermassive stars. And I show this example of this black hole, for instance, which is observed at a redshift of 7.54. So when the universe was 700 million years old, and it has a mass which is nearly 1 billion solar masses. So how you produce 1 billion solar masses in 1 billion years? You need very high accretion. And I know that Rafaela, for instance, has studied with her collaborators how the seed black hole can grow in mass up, starting from a seed black hole, which can be a stellar black hole or a more massive one, and go up for producing this very supermassive black hole at a redshift of 6 or 7. I am not myself, of course, I will not speak about this part of the history. Actually, I will rather ask how to produce the seed black hole at the beginning. Of course, there are some black holes that we can, as the one I just spoke about, which have a mass of 85 solar masses, but we can produce much more massive black holes by looking at the fate of supermassive stars. And this is the part I would like to discuss just briefly now. Actually, if we look at the way stars are formed in a mini halo, they are formed as stars at solar metallicity by accretion of mass, starting from a fragment, and the fragment will accrete mass. But what is different with respect to probably a star-forming region at solar metallicity is the accretion rate, because the virial temperature in mini halo is around 1000 degrees. This high temperature means a high density, because the virial theorem means that you have a hydrostatic equilibrium. So if you have a high temperature, you need a high density for, I would say, confine this matter in hydrostatic equilibrium. And the high density means a short free-fall time, so a high accretion rate. And the red line here corresponds to it is actually the track of an accreting object, which starts maybe with, let us say, a few solar masses. And then it shows how its luminosity and the effective temperature of the hydrostatic core vary when the mass is accreted, according to a law which is indicated here, and which is a fit to what is obtained in the hydro simulation by Yoshida from 2006 and 2007. But what is interesting, so typically a 20 solar mass star, a propulsion-free 20 solar mass star in this scenario, actually it will begin by accreting mass. At a given point, accretion will stop, because probably it may be for different reasons, but maybe the reservoir immediately surrounding this chunk of matter is empty. And when the accretion stops, the star will contract according to a Kelvin-Helmholtz time scale and become 20 solar mass stars on the zero propulsion-free, zero element sequence, which is shown here. So this would be, but of course, we can wonder what is the mass limit or the upper mass limit that we can reach in that scenario. And the answer is around 1000 solar mass, the order of 1000 of 900 solar masses here. And how we obtain this? Simply by saying that the maximum mass is can be said as the one at which the duration for the formation becomes equal to the lifetime of the star, because if it means that if these two timescales are the same, when you stop accretion, the star dies to some extent. So, and this is how you obtain this 900. Actually, here, to be honest, we computed until the end of the main sequence. So it's not really the end of the evolution for such a star. It will be a little bit more because we have the helium burning and the more advanced phase. But nevertheless, it will not change much because these advanced phases are anyway very short. So it gives an idea of what could be the most massive star. So it's around 1000 stars if we take this accretion scenario from hydro simulation. If we want to go toward more massive stars, we need a stronger accretion rate. And we can have them in what has been called atomic cooling halos, or maybe sometimes also in collision of chain of matter, of galaxies. And here I show you a plot where we look at the maximum mass, which is reached for different accretion rate, which are considered here as constant accretion rate. It covers typically 6 orders of magnitude of accretion rate. And typically, if we look, for instance, at an accretion rate of 0.01 solar masses per year, we have that this star will actually encounter an instability here just at the end of the main sequence. So here, there would not be further evolution, because here, in that case, you encounter what is called a general relativistic instability that has been studied by Eben and Chandrasekhar, which come from the fact that the radiation pressure becomes more and more important in such massive stars. Typically, in a 100,000 solar mass stars, at the end of the main sequence or toward the end of the main sequence, the beta, the ratio of gas to total pressure, is just a few percent. So it means that 98, 97% of the total pressure is due to radiation. And this tends to make, to destabilize a star. And you can see that if you consider, for instance, 10 times its accretion rate, you have a mass that will be at the maximum around 140,000 solar masses. If you still increase, you can see that the curve flattens, because you will encounter this instability at a still earlier stages of core hydrogen burning. You can also look at 10 solar masses per year accretion, and the curve will flatten, and probably we reach a kind of saturation. And probably with these processes, due to this instability, you can produce at most a few 100,000 solar masses, which is already a lot, of course. And these stars probably will end as massive black hole. How these stars will be in the Hesperus diagram, and here are exactly these kind of lines of accreting object. And what is shown here is typically the line of a star accreting at 1 solar masses per year. What is interesting is that above some accretion rate, which is around 0.01 solar masses per year, the birth line at a given point joins the Hayashi track. It does not join the zero-age main sequence as for the lower accretion rate, but it becomes a supergiant to some extent. It becomes a red star. And this is interesting, and you can see that the luminosity are of the order of 10 to the 9, 10 to the 10 solar luminosity. So it's very high. If we look at the internal structure of a 140,000 solar mass stars, I give you just a very rapid view. This is the temperature inside such a star, and this is the chemical structure as a function of the mass. Here it is as a function of the radius. Just a point, you have here a very small isothermal core at the end. It is not really at the end of hydrogen burning, but yes, hydrogen is completely depleted in the core. So it is at the end of the hydrogen burning. So you have an isothermal core, which is a few tenths of solar masses, and you have a huge extended and massive envelope. The tiny line here is a radiative zone, which separate the outer convective zone from the internal one. And what is interesting is that the temperature at the base of this convective zone is relatively low. It's of the order of a few times 100,000 degrees, lower than the burning, than the temperature needed to burn lithium, for instance, at the surface of deuterium. So deuterium and lithium will be cosmological at the surface of such a star, because they are not destroyed by the temperature at the base of this convective envelope. This would not be the case if the star would not be so red, I would say. It would not be a red supergiant. Okay, let me finish with a few minutes that remains by telling you what are the future perspectives. Of course, there are many. We need to improve convection, and for improving convection, a very, I would say, promiseful way is to try to extract from 3D simulation of convection some recipes to better account for the dependence on convection on the physics of the models. But I would like to here just mention also the question of the transport of angular momentum in stars, because I showed many examples where rotation had a relatively important impact. And actually, we know that the rotation it is accounted for in the massive star model I showed you, cannot reproduce what we observe in low mass star for the sun or for the subgiant or for the red giants. Actually, you have this, we have here this diagram where you have the evolution, where you have the core rotation as it can be deduced from asteroseismology for subgiants, for a large sample of red giants as a function of the surface gravity of these stars. If I use hydrodynamical instability due to rotation, I have the red line, which actually predict much too fast rotating core. So you need to extract angular momentum. And here, a model accounting for the Taylor-Sproyd dynamo, a little bit modified, which we call this model calibrated Taylor-Sproyd dynamo, do a much better job. It's not perfect still, but do a better job. And we have the hope that we shall get at a better version of this theory in order to reproduce this asteroseismic constraint for the low mass stars. And of course, we will apply the same physics to the high mass stars at different metallicities. Finally, I promised to give the last word to Leonardo. Actually, if I would retain an idea of what I showed, is that sometimes small changes, some details can change drastically the output of stellar models. And so the theme could be, or the main lesson could be, not to overlook the details. And the details are making the perfection, and as Leonardo da Vinci has written, and the perfection is not a detail. So I thank you very much for your attention.
Thank you, Georges. Thank you for this beautiful review on the many work that you have been doing with your groups and different mass scales, and for this last message. So that time is open for questions. I don't know if anyone from remote has interest in asking questions. Just switch on your mic or raise up your hands. In the meantime, I just to start, I would really like to ask so your opinion on this. We were starting to discuss this before the seminar. So on this recently detected magnified star at redshift 6.2. So what is your opinion on the properties that have been discussed in the paper, and how to better constrain these properties?
Oh, first of all, I think that it's a very challenging observation, and it's a wonderful luck to have just one star lensed by gravitational lensing. It's wonderful, and probably it's opened maybe the way to this kind of observation in the future, I would say. So first of all, it's fantastic. The second point, of course, we don't know so much at the moment, because I look a little bit in the paper. It seems that even the mass is not very well constrained. It goes from 50, but it can be a 500 solar mass stars. And of course, what would be interesting is to know the metallicity of such a star. It's even not known at the moment. We can just say that maybe, of course, they have some time, they will get some time probably from the James Webb. Maybe here we will get some more information. Anyway, it's a fantastic observation, yes.
So you haven't tried to fit it with your models yet?
So, there are not, actually from the paper, there are not enough constraints. Of course, if we plot our 500 solar track, we will have the same answer that what is presented taking the track by Selma Domingue. There is no big difference.
I see.
So we will get probably the same conclusion, yes.
I see. Okay, so any question from the audience, from people attending? Monica?
Thanks. The talk was really beautiful. I learned a lot, and I would really see your talk to to really keep in mind key concepts. I have one question which is related to the spin. What would be the spin you would expect from the relics of population 3 stars? You said that rotation can really change a lot the picture, and even an enhanced rotation can give you even a more massive black hole, as far as understood. And would this black hole, you would expect it to spin very close to the maximum spin allowed, or not? And since gravitational wave observations are indicated on average that the spins are not very large, 0.2 at most, would be the indication of a large spin of a low metallicity black hole?
Okay, these are very interesting questions. Let me say that, of course, we have the expectation, at least if there is no some strong magnetic braking, that population 3 stars will rotate it fast. It has been discussed by Stasi in the group by Fokker-Bohm. Of course, if there is a magnetic field, a surface magnetic field, it can slow down a little bit the star or couple it more to the disk when it forms, and so remove a lot of angular momentum. So it's very dependent. We don't know. But in case there is not this magnetic field breaking, indeed, population 3 stars are supposed to rotate very fast. Could it be that it produces fast rotating black holes? This is a more complex, I would say, question, because it depends on how, starting from a fast rotating stars, you can evacuate or not the angular momentum from the central region to the outer layers. And typically the models that I have shown have only hydrodynamical instabilities induced by rotation, which are not so efficient in making this job. So they will keep a lot of angular momentum in the core. While the Taylor-Sproyd dynamo, for instance, will remove much more angular momentum from the central region. And in that case, it can produce very slow rotation. Actually, there is a paper by Jim Fuller where he has a very strong theory, a very efficient coupling scenario for the transport of angular momentum. And actually, it produced nearly non-rotating black hole in that case. So I must say, we don't know so well the physics of this angular momentum transport. My view is that we need first to reproduce what we see in observed stars, in the sun, in the low subgiant and red giant of our solar neighborhood. And after, once we have identified the physics, to apply it for population 3 stars.
Thanks. If I may, I have a second question. Can I, Bella? So you said, interestingly, that the metal poor or metal free stars are far more compact. And so they are blue giant more than red giant in a sense. So suppose you have two stars in a binary system. The common envelope phase is still there, or since they don't have these bloated envelopes, you might miss the process which is reducing the orbital period in order to make them potentially gravitational wave sources merging on a time scale which is comparable to the then Hubble time. So we would like to see a merger at redshift 10 or so.
Okay, so this is again a very good point. Actually, it's true that the population 3 stars remains more compact. And of course, to have a common envelope, it's better when the star is become a red supergiant, typically. If you don't have a red supergiant, probably it's a bit more difficult to have this kind of process. Myself, I don't know so well to answer your question, because I am not making close binary evolution on my own. But what I can say is that the fact that the stars are more compact probably makes the condition for having it much more severe. You have to start from more nearer stars, you see.
Yes.
On the other hand, a point on which we have worked with Boyan Liu and Fokker-Bohm is the demography of binary stars in the first clusters formed in mini halos. And we got, I think, an interesting point. Actually, you know, if you start from a cloud, which form this cloud will probably have a little bit of rotation because it is surrounded by halos of different mass and not in isotropically distributed. So there will be some torque that will give to this cloud a small rotation. When the cloud collapse or when there is sinks inside that cloud, which are the forming stars, they will have some angular momentum from the outer part of the cloud, bring in the interior. But this angular momentum is too much with respect to this object, with respect to the dynamics of the central part. And in order to join, I would say, Keplerian velocity or more natural equilibrium, they have to go away. So you see that if we keep the conservation of the small angular momentum of the cloud, and we say that all this angular momentum will finish in the orbital angular momentum of the stars, actually we obtain that we have a very extended cluster. And in this extended cluster, the number of closed binary is very small.
It's very small.
Of course, if we have some dissipation of, if we take some part of the angular momentum from the cloud and we put it elsewhere, in that case, you can have much smaller size for the cluster and having much more closed binary black hole.
So you suggest that the initial radius of the binaries that might form is so large that they will never be binaries. And so not seeing high redshift events might just tell us that these binaries are not even forming. And so it will be extremely difficult for them to correct.
At least in the paper by Boyuan, they say that most of the binary black hole, which could be observed merging by the gravitational wave emission from population 3, would come from a tightening due to a dynamic interaction with a third body.
Yes, but then it's complicated to have so many bodies, the density to them harden to the extent to have very short lifetimes. So thanks a lot.
Okay, thank you very much, George. Is there any other question or curiosity? Actually, I was interested by your result on the pair instability gap. So the fact that if you, because it's somehow, I don't know if you have tried to compare this with other models. So for instance, the models of Marco Limongi and Alessandro Chieffi, who seem to find a kind of opposite trend. So if you increase the rotation, essentially you meet the pulsational pair instability easier than it's easier to meet the pulsational pair instability than for non-rotating stars. So actually what they conclude from at least their grid of stellar masses and rotation rates is that in order to form more massive black holes, you have to avoid the star to be rotating. So I don't know if you have compared with the results.
Actually, I would say I would not. We would get similar results because the star I showed was a 250 solar mass, which is in the upper end. I would say.
No, sure.
But of course, for the lower end. Here, it's probably the case that is studied in this, if I remember well, in this paper.
Yeah, they go up to, I think, 100 or 120 solar masses, yes.
And in that case, indeed, rotation by making the core bigger for a given initial mass can lower the limit in which the pair instability is produced. And this, I would say, is quite reasonable, absolutely. But the case of this 250 is a bit counterintuitive because we have the reverse due to the effect of mass loss, I would say.
Okay, yes. So it's the effect of rotation which changes depending on the mass that you are looking at.
Exactly, absolutely.
And then the problem is how to how to make predictions on how the rotation rate correlates with the mass. Of course, this is very complicated.
But I suspect, this mass gap is something that is anyway very dependent on the model physics, and it should not be taken too, I would say, strictly. It probably depends a little bit on metallicity. While some people say it does not depend on metallicity, I don't think so. I think it depends also on the metallicity, on the rotation. And so it's not so. I think it was funny to see how many papers have appeared.
Yes.
And much more ideas than maybe.
So if I can translate what you're saying, it has been taken too seriously.
maybe a little bit, I would say. Of course, the general idea is probably correct, but now the numbers can be quite difficult to establish.
Yeah, but of course, this provides additional constraints for stellar evolution models, which is always important. Okay, so please go on.
I wanted to say that, especially that, we have no real true candidate, it seems, for pair instability supernovae. Also, there is one candidate, and I remember it was Paolo Mazzali who has studied it, 2006 if I remember well, but I am not sure of the name. Anyway, it was a good candidate, but it's not even sure that we have seen any pair instability supernovae.
Yeah.
I am sure they exist because the physics is relatively straightforward, I would say.
Yeah. And chemical imprints also are difficult to identify, right?
Exactly, yes.
Okay, so thank you very much, George, for. Sorry, I have a question from Dominic here. I was forgetting.
Yeah, no, thank you. Yeah. In principle, you mentioned already there's many uncertainties in the models. Of course, even like nowadays for present-day stars, like concerning rotation and magnetic fields and similar things. One thing I wanted to understand more specifically, I mean, you had this interesting result for very low metallicity stars that in the absence of rotation, I believe there was the pair instability explosion. And with rotation, I believe it was forming a black hole. And I had a question like, how generic is this result? So does it require a specific amount of rotation or a specific distribution of the angular momentum inside a star, or is it very generic, like how much does it depend on the differential rotation on magnetic fields? Can you say something about it?
I can say that probably it's not generic. I would say it's an example of the impact of the physics of rotation on the evolution of a 250 solar mass stars. But I cannot pretend that it is the evolution of most of this type of stars. My view in this respect is the following one. Actually, we know that the angular momentum transport in these models has some weaknesses. By the way, they have some weaknesses, but the Taylor-Sproyd dynamo has also some weaknesses. Typically, I give you just an example. The fact that, for instance, if we take a beta Cephei stars are 9 solar mass stars. Thanks to techniques asteroseismologic applied to this kind of stars, we can have an idea of how the star is rotating. And the star is rotating differentially, with the core rotating faster than the envelope. And these models that I showed you can well reproduce this. While if you take a Taylor-Sproyd dynamo, it will produce a flat rotational profile. So what I would say, the models are probably representative of some physics governing the evolution of some families of massive stars, maybe the slower rotators, maybe some stars which, for whatever reason, miss the activity of the dynamo. While the Taylor-Sproyd dynamo probably will cover a bigger population of stars, I guess, but maybe not all. So as always, we are a little bit in a stage where we are looking, searching, trying to compare with observation and trying to get a kind of a general picture from that. But my view is that we need more than, nature is more rich in physics than our models to some extent.
Luckily.
Yes.
If I can ask a follow-up question, you've also previously referred to the Taylor Sprout dynamo, and this is also something I'm interested to understand better. I mean, I've seen often also in the literature that people often adopt this model. Is that because it can be more easily incorporated in these types of calculations, or is there another reason for it? Since I think in principle, I mean, even for M dwarfs or for the Sun, we still have many open questions on the right dynamo models, and so also just to understand why specifically the Taylor Sprout dynamo.
It is based on actually an instability of the magnetic field, which has been shown a long time ago by Taylor. And Sprout has advocated that it is the instability which grows the faster and which dominate all the others. It's why he pushed in this direction. And in his paper of 99 and 2002, if I remember well the dates, actually he provide the diffusion quantities that can be incorporated in 1D model. So I would say there are two reasons for the success of this model. On one side, the fact that it is based on a well-known instability of the magnetic field that seems to overrule all the others to some extent. And the second, it has get expression for incorporating into the models. Now you know that there is also Jim Fuller who has proposed a kind of variation of this Taylor-Sprout. I would say it's not so different from the Taylor-Sprout dynamo. The main difference is in the time scale of the growing up of this instability, which is longer in the Jim Fuller theory, if I remember well, and allows to reach higher magnetic field and thus to still produce a stronger coupling. But it's interesting to say that there are some way of disentangling between these two theories, because typically, if we apply this to a solar model, the solar model should rotate as a flat solid body rotating up to the center, while Taylor-Sprout theory, which is less efficient when there is gradient of chemical composition, present, I would say, a small core rotating a bit faster than the envelope. Of course, we don't know how the core of the sun is rotating, and so we cannot disentangle between the two, but there is a hope that in the future it will be. Moreover, according to work done by Patrick Eggenberger in Geneva, the Jim Fuller theory cannot accommodate very well for both the subgiant and the red giant at the same time. So now we are still looking for a better physics for this transport mechanism. And what we would like is to have identify the best physics and then to use it, of course, to make massive star evolution.
Yeah, great, many thanks.
Okay, so thank you very much, Georgia, for this wonderful seminar and for the time spent with us with many questions. And I thank all of you for participating to this